Hey guys, today we are going to be discussing a clip from the NonSequitur Show from March 2nd, 2019. This clip comes from a debate between Godless Engineer and Antonio Subirats and covers Antonio Subirats' claim that objects should accelerate faster on the moon's surface than on the Earth due to the reduced 1/6 gravity on the moon. Godless Engineer and Steve McRae did a great job repeatedly answering his question, but Antonio continued to make the claim. While Godless Engineer and Steve McRae were both right, they forgot one key point. Antonio Subirats is a flat earther, and flat earthers are fucking idiots. So we will be playing a few clips from the show, but not the whole thing. I highly recommend watching the whole debate, as it was, in my opinion, a very entertaining show. Be sure to subscribe to Godless Engineer, Steve McRae, and the NonSequitur Show if you haven't already. Links to all the channels and videos will be in the description.
I don't know why this is difficult for you, Antonio. The mass of the moon is different than the mass of the Earth. If you understand the law of gravity
slowly. Why is he going slowly?
If you understand the law of gravity, which is the measurement of force, which is big G,
slowly. The law of gravity doesn't explain why he's going up.
I'm explaining
slowly.
it. I'm explaining this.
Go ahead.
So the question that was asked by Antonio Subirats to Godless Engineer is, why don't things accelerate faster leaving the moon's surface because of the reduced gravity pulling objects back down? Now, at first glance, this is a pretty good question. If an object experiences less gravitational pull at the point it leaves the moon, shouldn't it move up faster and fall slower? But the answer is no, it shouldn't. So strap on your safety hats and let's talk physics. The first thing that must be understood is that Antonio Subirats does not understand Newtonian physics. And for this explanation, we are going to assume that the only force acting on an object is gravity. To achieve the process of leaving the ground and going ballistic, an object must generate a force opposite to the pull of gravity holding it to the surface. And the amount of force is directly responsible for the initial velocity of the object leaving the surface. Once the object leaves the surface, the only force acting upon it will be a constant downward acceleration of the moon's gravity. There's a really complicated way of calculating this initial force, but there's also a really simple way of calculating it. Since the object is under constant acceleration towards the surface of the moon, the time it takes to go from the ground to the apex of the jump is equal to the time it takes to go from the apex to the landing. It is also worth mentioning that the velocity and force at the moment of impact is the same as the moment of liftoff. So now that we've gotten that out of the way, let's do some calculations to determine what is actually going on here. The impact velocity can be calculated by the equation v equals initial velocity, which is 0, plus acceleration times time. Using Antonio Subirats' own video, we can calculate the time from apex to landing, which lasts for 23 frames at 30 frames per second, to be approximately 0.76667 seconds. So given the moon's gravitational acceleration of 1.62 meters per second squared, we can calculate the impact velocity by multiplying 0.76667 seconds by 1.62 meters per second squared to get a value of 1.242 meters per second. As discussed previously, the impact velocity is equal to the liftoff velocity, and that is the reason they are going up slow and coming down slow. There is no magic or video editing necessary. Godless Engineer and Steve McRae were right, and Antonio Subirats is a fucking idiot. But how much fun is a short video? Let's go ahead and do our own video analysis to see how closely the scientific consensus matches to what we can observe. Let's start by visually calculating the gravitational acceleration at the moon's surface. Keep in mind, these are only visual estimates, so my numbers may be off a bit due to estimations and limitations. We know that John Young was 5'9" or 1.7526 meters tall, so we can estimate the top of his head to be about here, and the bottom of his boot to be about here. The total measured distance between these two lines is 705 pixels, and the distance measured from apex to landing is about 189 pixels. We can do an easy conversion to show that the visually measured distance from liftoff to apex is approximately 0.4699 meters. Now we can estimate the acceleration of the moon with the same formula we used a moment ago. D equals 1/2 AT squared, except this time we have D at 0.4699 meters and T at 0.76667 seconds. Rearranging the equation, we get 2D divided by T squared, or 1.5989 meters per second squared. Comparing that to the scientific consensus of 1.62 meters per second squared, we get an error of only 1.3%, and this was done from simple observations and math alone. Get wrecked, Subirats. You're a fucking idiot. Now, math is fun, guys, and just to show you, I am going to challenge you, the viewer, to a math question. According to historical record, John Young and the Apollo spacesuit had a combined mass of approximately 163.2 kilograms. Given the information in the video, can you calculate the force the astronaut jumped with? And using that force, can you calculate what height he would have achieved if the jump took place on Earth? I encourage you to do the math yourself, and don't just use someone else's answer. Leave your answers in the comments below, and in a couple of days I will upgrade the description with the correct answer. Well, I appreciate you guys sticking around for this short video. Be sure to like, subscribe, and click the little dinger if you haven't already. Good luck with the math challenge.
For the record, I just want it on record that this is more painful than the first time I tried anal.
I'm Father Skeptic, and I'm out.